Say, I want to show you two problems which are it's kind of interesting to me. I've always liked them, and they're kind of in a way reverse of each other, but I'll show you what I mean, or coming from the reverse direction. But I'll show you exactly what I mean. So you want to build a rectangular enclosure, the rectangular enclosure, and of 25 square feet. Oops, I wrote feet squared. 25 square feet. Square feet. Okay. And you want to use minimal fencing. So what does that mean? You have a rectangle here, and the area is 25. Now it could be shaped like this. It could be, long and tall. It could be wide. There's all different. As long as the area is 25, that's what I need. So the fact that's a given, that has to be. I must have a 25 area. Um, whatever reason. If it's for sheep to graze in, I need 25 square feet of grass so they don't starve. Whatever it is, whatever the reasons are, I need 25. It has to be 25 square feet, whatever the reasons are. So this is my constraint. Means this is immutable, it's unchangeable constraint. I must have that 25 square feet. This is my constraint. And the what's the constraint equation? Well, if the side is x and the other side is y, which means that's x and that's y. So the constraint equation is that xy equals 25. Okay. Now, what is it that we want? We want to minimize the amount of fencing I use. So in other words, another way of saying this is that I want a rectangle whose area is 25 and the perimeter of the rectangle should be a minimum. Meaning if I add up the four sides, it should be a minimum number, because I want to use a minimum amount of fencing. So what is the perimeter? Funny you should ask. The perimeter, that's equal to 2x plus 2y. And so this is the objective equation. Because my objective is to minimize the perimeter. And what I'm going to have to do, though, is the problem is I have two variables. I have an x and a y. So I don't like two variables. I'd rather have one variable. So I'm going to solve for y in terms of x and divide both sides by x here. And y equals 25 over x. I'm going to take this and substitute it into this y. So this is going to become 2x plus 2 times 25 over x. So my new objective equation is p equals 2x plus 50 over x. And now I want to get the I want to find the minimum, so I'm going to have to take a derivative. That's what happens. You take derivatives, and I get p prime equals 2 minus 50 over x squared. So I'm going to set this equal to 0. Which is going to give me 2 is equal to 50 over x squared. And then I sort of cross multiply, if you will. And I get 2x squared equals 50. And divide by 2. And I get x squared equals 25. Now, there's no positive, no negative. It's because, I'm sorry. There's no possibility of a negative value here, because we're talking about a physical object. We're talking about a physical, rectangle, physical fence. So as far as plus or minus 5, forget plus or minus 5. It's just x equals 5. Now, if x equals 5, and y is equal to 25 over 5, so y equals 25 over x equals 25 over 5, and equals 5. So I get x equals 5 and y equals 5. Now, before I celebrate too much, I need to test that this is indeed a I need to test that this is indeed a minimum. So we're going to have to do, well, again, I'll either do the first derivative test or the second derivative test. In this situation here, since p prime is 2 minus 50 over x squared, I think I'm going to do a second derivative test. So I'm going to do the second derivative test. And we're going to take p double prime, and that's equal to positive. Let's just write this out. P double prime is going to be, well, again, let's rewrite p prime. I want to rewrite p prime. Let me just I want to rewrite p prime with exponents. 2 minus 50 x to the negative 2. So p double prime is equal to negative 2 times negative 50 times x to the negative 3, which in other words, p double prime is equal to positive 100 over x to the third. And clearly, if I want to find what is p double prime of 5, that's just equal to 100 over 125, which is which equals 4/5. But more importantly, or more to the point, it's greater than 0. So greater than 0 means that it's concave up, which means I have a minimum. So concave up, and have a minimum. And there we go. Now I find this kind of interesting that the most efficient, if you will, rectangle winds up being a square. The most compact, if you will. I guess it kind of makes sense. You know, squares are kind of compact, and you know, it all fits. So once again, if you're building a rectangular enclosure and it's going to be 25 square feet, a square is going to give you the least amount of fencing necessary to achieve that area of 25. Now I want to do a second problem, and it's kind of the flip side of the first one, because the first one we set the area was 25. We wanted to find the minimum perimeter. Now what I wanted now instead of setting the area and finding a perimeter, we're setting the perimeter at 28 feet, and we want to find the maximum area that I can get from that 28 feet. So I want to sort of get the biggest bang for my buck. So I have 28 feet of fencing, and I want to build this enclosure so it's the most area for whatever reason. Whatever reason I need it to be the most area. Anyway, let's see what we got here. So I'm building a rectangular enclosure of maximum area using 28 feet of fencing. So let's so basically my fencing, let's put it this way. So my fencing is going to be in a rectangle. That's going to be x. So I have x and I have y. And I know that the perimeter, 2x plus 2y, that has to equal 28. And that's my constraint. Meaning that I always, the perimeter is set. The perimeter is 28. That's how much fencing I have. That's how much material I have. And that's not changing. But I want to proportion it, or I guess make the dimensions, the optimal dimensions, that the area becomes the maximum. And so it's kind of like a similar problem to the previous problem, but it's kind of going like in the opposite direction, if you will. Anyway, that's my constraint. Now, what is my objective? My objective equation is the area is equal to xy. We know that. I knew that. You knew that too. A equals xy. And I want to take a derivative, but I have two variables here. How do you take a derivative with two variables? Well, there are ways, but here's what I'm saying. I want to go back to my constraint equation, and I want to solve for y in terms of x. So I'm going to subtract 2x from each side. And I get 2y equals 28 minus 2x. And I divide both sides by 2. And I get y equals 14 minus x. So I'm going to take this 14 minus x, I'm going to substitute in for this y. So a is equal to x times 14 minus x. And of course, that equals 14x minus x squared. Now I want to make a note that the area is an upside down parabola. So right away, I know that when I'm going to try to find the vertex or the maximum, which is a vertex is a maximum, and but I can tell you right now that it's going to be a max because this is upside down parabola, so therefore it's going to be the highest point on the parabola. But let's just solve it. A prime is equal to 14 minus 2x. I'm going to set that equal to 0. So I get 14 minus 2x equals 0. 14 equals 2x. And, of course, x equals 7. Now, if x equals 7, and y is equal to 14 minus 7, so y is equal to 14 minus 7 equals 7. Look at that. We have a square. So it turns out that that just is the most efficient thing. I guess that's I guess nature likes a square. That if I have a given perimeter and I want to maximize the area, I use a square. If I have a given area and I want to minimize I make it a square. So I always found that cool the way that works out, and this works out also. And but that's all I wanted to show you. So it's again another application of applied optimization, and I always just found this square thing very fascinating. Anyway, that's it for today. We'll by the way, if you had to make a box and you want to again use the minimum material and the maximum volume of the box, would a perfect cube be the answer? You see what I'm saying? As opposed to any other kind of box? Well, guess what? We're not going to do it in this class. We're not going to do it right now, but the answer is yes. It would work for a cube as well. So it's kind of it's always I don't know why it just it's something which has always been fascinating to me. Square-like things just very efficient. Anyway, this is me signing off, and we'll see you guys next time. Bye.